Welcome to chapter 8.1. This section is about linear systems of differential equations. Now, as you know, in the first part of the ordinary differential equation course, we talked about first order linear differential equations. And here we have only one dependent variable x of t. And this a of t is a coefficient of x, and sometimes this a of t can be a constant. Then we have a constant coefficient differential equation. Okay. And if we have a differential equation where this right hand side f of t equals to 0, then we have a homogeneous differential equation. Now in this section we are going to consider a system of differential equations that has more than one dependent variable. Now here are some examples for systems of differential equations. Now in the first example we have two unknowns, x1 and x2. And in the left hand side we have the derivative of x1, and in the right hand side we have the relationship between the derivative of x1 with the dependent variables x1 and x2. Now 2 cosine t is a coefficient of x1 and sine t is a coefficient of x2. Similarly, the derivative of x2 equals to 3 sine t x1 plus 5 cosine t x2. Therefore, the coefficient of x1 is 3 sine t and the coefficient of x2 is 5 cosine t. In the second example, we have a similar second order differential equation. So first order differential equation with two unknowns. But now in this side we have e of t and t e to the power t, which represents the little f functions that we discussed here. Therefore, this second example is a system of non-homogeneous first order differential equations. Now finally we have a system with three unknowns or three dependent variables, and as you can see this is a homogeneous system of first order differential equation. Now in general, let's say we have n number of dependent variables, then the corresponding system can be expressed in this form. And as we can see, we have these function f1, f2. Therefore, this is a non-homogeneous system of differential equations. And each of these aij functions denote the corresponding coefficient of the variable. So as an example, the coefficient of x1, here it is a11 of t, some function of t. And in the second equation, coefficient of x1 is a21 of t. Now in this course we represent a system of differential equation using a matrix notation. And so basically what we do is this: we arrange the dependent variables in a column vector. So this is a column vector. The first element is x1, second element is x2, and so on. Therefore the last element is xn. So this is a column vector, and we denote this column vector using x of t. And the coefficients of the dependent variables can be put into a matrix which is a of t, and we call this matrix a of t as a coefficient matrix. The non-homogeneous terms can be arranged into a column vector. Again, this is a n by 1 column vector because it has n number of rows and 1 column. Okay, so similar, this one is n by 1, but this matrix is n by n, and again this vector f is n by 1. Now in a more compact form, we can represent this differential equation in the following form. Here we have the derivative of this vector x of t equals to our coefficient matrix A of t times the vector x plus the non-homogeneous terms. So if this part equals to 0, if f of t equals to 0, then we have the homogeneous system of differential equations. Okay, now whenever we have a system of differential equations, we try to use the matrix notation, and you will see the reason later. Now let's say we have a system of differential equation like this: x1 prime equals to 3x1 plus 4x2, x2 prime equals to 6x1 minus 7x2. So as you can see, we have two dependent variables. Therefore our vector x, if you think about the vector x, it has two components, x1 and x2. And in the right hand side, we have the derivative of this vector x equals to, now if you think about the left hand side, we should have the coefficient matrix A here, and then the solution vector x, or the dependent variable vector x. Now this is the way we obtained the coefficient matrix. This first element corresponds to x1, that's the coefficient of x1, which is 3, and then the second element corresponds to the coefficient of x2. So whenever you multiply this matrix and this vector x, you should get this first equation. As you can see, you will get 3x1 plus 4x2. Similarly, the second row of this matrix A contains the element 6 and negative 7. So this, in this case, your coefficient matrix is a constant matrix. Okay, here we have a system of non-homogeneous first order differential equations. Again, in the left hand side, we have the derivative of x1, x2 and x3. Those are the dependent variables. And we have a coefficient matrix A and the vector x plus, now this time we have this non-homogeneous vector f. So this first element is a coefficient of x1, then we have the coefficient of x3. We do not have x3 term in the first equation, therefore the coefficient of x3 should be 0. Similarly, we can fill the remaining elements, and these non-homogeneous terms does not involve the dependent variables. That is why we separated those non-homogeneous terms into a vector f. So the first non-homogeneous term is minus 9t, then we have 7t squared, and finally we have minus 6t plus 7. So this is the matrix form of this differential equation.